Okay, let's get started. So, um, there is some deltas here. Okay, so last time I think we are stopped at the place at so suppose that this one N2 is positive, and second we have this W1 is equal to 1, and then W2 is equal to -1 plus I. Okay. And then we say that, okay, so yeah, and then we want to show that when, okay, so we have the case when, so yeah, so we have already did the case when the N2 is N1 is bigger, what do I want to say? So N1 is less than N2, right? I think this case N2 is bigger, so yeah, I think we are done with this case. So, and then what happened? Okay, so now what happened if when N1 is bigger than N2? Okay. Yeah, so that means that, yeah, so here we have the N1, okay, and then we have minus N2, so maybe here this is N2, and then, so this is N1 minus N2, and then, so this is and the height is just N2, right? Okay, so, yeah, so I think we fix N2. And then we say that, okay, so what happens if this N1 is getting bigger and bigger? Can we get a lower bound? Okay. So question, when this N1 is getting bigger and bigger, can we get a lower bound for the quantity square root of N1 minus N2? So this is strictly positive, and then plus N2 squared, lower bound for this one as some constant times N1 plus N2. Okay. Let's see. So okay, so yeah, so you may imagine that when this N1 is getting bigger and bigger, right? The ratio N1 and N2 is really close to N1, right? So roughly speaking, okay, so okay, I think the idea is that so as N1 is goes to infinity, then this N1 minus N2 is strictly dominating the N2, right? So and then okay, so then this okay, so this roughly speaking, so this is just this becomes N1, right? As N1 goes to very, very large. So yeah, so I want to say that, so no, this is not really approaching to N1. But it is like, so the ratio between this one and N1 is really close, okay. So, and then for this K times, yeah, intuitively speaking, okay, and then so this one is also like N1. So okay, so what I'm guessing is that so I'm guessing is that this K is really close to 1. Okay, so okay, so no, let me make it clearly. So yeah, because yes, because you can always make the K large. Sorry, K like small, such that the N1 plus N2 is strictly bigger than this N1 minus N2, right? So choose. So may choose. Let's say K. Maybe let's say K equal to 1/2, okay? Because we choose it at the beginning, right? So then, okay, so then when, okay, so when, so remember we are fixing N2, okay? So basically, so when this, okay, so when N1 minus N2, okay, so N1 minus N2 is like the lower bound for this term. Is bigger than or equal to the 1/2 N1 plus N2. Then we're done. Okay, so then we are in a very good shape, right? So it's definitely true when N1 is strictly bigger than this N2, right? Yeah, when N1 is really large. So okay, so how large does it need to satisfy the condition? So it's definitely not true when N1 is equal to N2. So let's say that when this so we are okay. So maybe what we want is what we want. Okay, so here, let's say that let's say that N1 equal to wait, N1 equal to 2 N2. Does it work? So then on the left hand side you will have N2, and then on the right hand side you will have 3/2 N2, right? This doesn't work. So let's see, let's change another one. So okay, I think maybe let's say 3 N2, and then this is 2 N2, and then this becomes, oh, this becomes equal. Okay, yeah. Okay, so let's prove it. So when this n1 is bigger than or equal to these 3 and 2, right? So then the left hand side is then the n1 minus n2 is bigger than equal to wait, shoot, how are you gonna say? Okay, n1 minus n2 is bigger than equal to 2 n2, right? And then what about the left hand side? Oh, I think maybe I can prove it in this way. Okay, so let's say that this n1 is equal to k n2. So then what we have is that we have the n1 minus n2, right? So n1 minus n2. So the left hand side is just the k minus 1. And then the right hand side is 1 plus k. Okay, so so let's say that. So let's multiply by 2 on both sides. Okay, so 2k minus 2, and then the other side is k plus 1. Okay, so then you move it to in order for this to hold, right? So I want this to hold. Okay, so then I move the k to here, and then k is bigger than equal to 3. Okay. Does this hold? So when k is bigger than equal to 3, then you do what? Yeah, you add a k on both sides, right? And then okay. So yes. Okay, so this is true. Okay, so then okay. All right. So so this is true. So what happened? So what happened if k is between 1 and 2? Okay. Right. So so now the question is, what happened if this k is between 1 and 3? So the question is, so if this k is between 1 and 3, then what happened? I think you can do something with the stuff here, right? Because this k is limited. I think you can get something. Let's try. So so here, I think that's a really good way to really analyze this stuff. So so let's try this. Let's try this. So then okay, so then you have the square root of, so let's just substitute the n1 by k n2, okay. So, yeah, so where am I? Yeah, so just do that, okay. So then, like L, yeah, I defined it, let L to be this guy, okay. So then L is equal to, let's say k n2, and then plus, sorry, minus n2 squared plus n2 squared. Okay. So let's see. Then this is equal to, yeah. So you can definitely pull out this n2, right? Because it's positive. And then for the, yeah. So and then for then what you get? It becomes k minus 1 squared plus 1. Okay. So then it is equal to n2 times k squared minus 2k, right? Oh, yeah, sorry, I think I shouldn't use k because I'm using the k for this one. Okay. So, okay, never mind. So I think, yeah, so maybe I'll just use another letter later, okay. So, and then on the left hand side, what we have is that we are having this, maybe I use, yeah, it's just really bad, I think. Yeah, let's switch it to C here. Okay, sorry. Okay, so yeah, so this is okay. So on the left hand side, we have some constant. Maybe let's omit the constant first. So k and 2. So k plus 1 and 2. Okay. Okay, so okay, so what I want is that I want this k squared minus 2k is bigger than the k plus 1 squared, which is k squared plus 2k plus 1. Oh, sorry, this may not be true, but over some constant. Yeah. Okay. Yeah. So. Yeah. So. Yeah. So. Yeah. I guess maybe I think. Yeah. Yeah. I'll put it this way. So. Okay, so here we just care about this case between 1 and 3, right? Okay, y is 2. Okay, so let's see. Let's okay. Does this say that this k is positive? Okay. Okay, so I think there's the assumption that this k is positive. Okay. So let's see. Let's multiply by c on both sides. Yeah, otherwise if it's negative then it's trivial, right? Yes, okay. Okay, I know that this k is between 1 and 3, right? So, okay, let me think. So, okay, yeah. So, does this works? Okay, so let's use a substitution of variables. So, um, okay, so let me just delete that. Then this becomes so then we want is that if we have sk squared minus 2s k minus 1 is bigger than 0. Yes. Okay, so we want to is this one factorizable? I don't think it is factorizable. Yeah, otherwise, wait, shoot. Okay, so let's analyze this one. Okay, so okay, so the thing is that we don't know whether it's as positive or negative. Okay, so let's draw this one. Yes, so let's draw this one. So does this has any zeros? Yes. Yeah, we want to sketch a graph. Okay, so can we solve? Okay. Yeah, so it's a parabola. So with the variable k, when k is between 1 and 3. So yeah, so let's use the quadratic formula. So okay, this is just scratch, okay. Yeah, so let's see. So yeah, so we kind of implicitly assume that this S is kind of positive. Yeah, so So we have, let's make it inside. Oh, actually these two cancel out. So it becomes 1 plus 1 over x. Okay. Okay, so these are the roots. And then since this parabola is going up, right? So yeah, suppose s is positive, then parabola is going up. Then okay. Okay, so we want to see such that this whole thing is bigger than 0. When k is between 1 and 3, right? Okay. So then, so this graph actually looks like, for example, this is like 1, and then plus or minus square root of 1 plus 1 over s. So I will imagine that it has something like that. But what happened? So what like yeah. I mean, I mean, like, okay, so say you have s equal to 1. Okay, so we have k squared minus 2k minus 1. So if you plug in 1, then it's less than 0. Plug in 3, then it's bigger than 0. Okay, so what happens if you plug in 1 here? Okay, so if you plug in 1 here, then you have s minus 2, s minus 1 bigger than 0. gotta. Oh yeah. Okay. So. Why this doesn't work? Let me think. Okay, so let's look at the graph. Okay, let's look at the graph. So, um, so what does it really mean if this cape is between 1 and 3? So, this means that okay, so apparently when this k is equal to 1, so what happened is that this N1 plus N2 is like really small, right? Okay, let's try that. Let's maybe okay, maybe let's keep it. Okay, so okay, so when is k equal to 1, so you have just the N2, right? So then you have and at the same time you may have the N1 and N2 really close to each other. Wait. Wait. Okay. Okay. So. Oh. Okay, so okay. Okay, so I think, so because, so this is definitely bigger than, so bigger than equal to, n2, right? And then you can make the k small such that, this guy is actually less than n2, right? So how would you make the k small? So so you can make this k equal to, so you can make this k equal to 4, right? So if the k equal to 4, then you may have the, because n1 is between n2 and 3n2, so if you divide by 4, then it at most 3 over 4 n2, and then this n2 is at most, it is n2, so the whole thing is at most n2. Okay, so okay, okay, so now, okay, we want to analyze the, okay, so if we drop the condition, for the W1, right? Okay. So if we drop the condition for W1 equal to 1, so what would happen? Okay, so now, we assume, Yeah, so we assume this. Yeah, so okay, yeah, let me think. So this x1 cannot be equal to 0, right? Yeah, this x1 cannot be equal to 0. I think that's what's going on here, right? Okay, so okay, yeah, so let's I think this x1 is yeah, otherwise if you have 0, then you may have the modulus. Oh shoot. I think in reality this x2 can be equal to 0, right? But here we are assuming that it's bigger than 0. Okay. Okay. So okay. Okay. So yeah, let's continue. Let's continue next time. Okay. Yeah.